Lab 15, Calorimetry and Hess's Law. A man working for a cleaning firm was told by his employer to pour some old cleaning supplies into a glass container for disposal. Some of the supplies included muriatic or hydrochloric acid, HCl in aqueous form, and a drain cleaner containing lye or NaOH in solid form. When the substances were mixed, the container shattered, spilling the contents onto the worker's arms and legs. The worker claims the hot spill caused burns, and he is therefore suing his employer. The employer claims that the worker is lying because the solutions were at room temperature before they were mixed, and that tests after the accident revealed that the mixture had a neutral pH, indicating that the hydrochloric acid and sodium hydroxide were neutralized.
Like he's totally lying. NaOH or sodium hydroxide is just lye. People have used it for centuries, and it's a common ingredient. And there's oven cleaners and drain cleaners. It's totally safe. HCl or hydrochloric or muriatic acid is, well, an acid, but it's commonly found in things like tile and toilet bowl cleaners. People use it all the time. It too is totally safe.
The court has asked you to evaluate whether the worker's story is supported by scientific evidence.
Let's get to the bottom of this.
Chemicals can be dangerous because of their special storage needs. Chemicals that are mixed and react are even more dangerous because many reactions release large amounts of heat. Glass is heat sensitive and can shatter if there is a sudden change in temperature due to reaction. Some glassware, such as Pyrex, is heat conditioned, but can still fracture under extreme heat conditions, especially if scratched. You will measure the amount of heat released by mixing the chemicals in two ways. First, you will break the reaction into steps and measure the heat change of each step. Then you will measure the heat change of the reaction when it takes place all at once. When you are finished, you will be able to use the calorimetry equation from the chapter Causes of Change to determine the following: the amount of heat evolved during the overall reaction, the amount of heat for each step, the amount of heat for the reaction in kilojoules per mole, whether this heat could have raised the temperature of the water in the solution high enough to cause a burn. First, we'll draw our data table. And familiarize ourselves with our calorimeter. Pour about 100 milliliters of distilled water into a graduated cylinder. Measure and record the volume of the water to the nearest 0.1 milliliter. Pour the water into your calorimeter. Measure and record the water temperature to the nearest 0.1 degrees Celsius. Determine and record the mass of a clean and dry watch glass to the nearest 0.01 grams. Remove the watch glass from the balance. While wearing gloves, obtain about 2 grams of sodium hydroxide pellets and put them on the watch glass. Use forceps when handling sodium hydroxide pellets. Measure and record the mass of the watch glass and the pellets to the nearest 0.01 gram. It is important that this step be done quickly because NaOH is hygroscopic. It absorbs moisture from air and increases its mass as long as it remains exposed to air. Immediately place the sodium hydroxide pellets in the calorimeter cup and stir the solution with a stirring rod. Do not stir with a thermometer. Place the lid on the calorimeter, watch the thermometer, and record the highest temperature in the data table. When the reaction is finished, pour the solution into the container designated by your teacher for disposal of basic solutions. Be sure to clean all equipment and rinse it with distilled water before continuing with the next procedure. Pour about 50 milliliters of 1.0 molar hydrochloric acid into a graduated cylinder. Measure and record the volume of the hydrochloric acid solution to the nearest 0.1 milliliter. Pour the HCl solution into your calorimeter. Measure and record the temperature of the HCl solution to the nearest 0.1 degrees Celsius. Pour about 50 milliliters of the 1 molar sodium hydroxide solution into a graduated cylinder. Measure and record the volume of the sodium hydroxide solution to the nearest 0.1 milliliter. For this first step, rinse the thermometer in distilled water and measure the temperature of the NaOH solution in the graduated cylinder to the nearest 0.1 degrees Celsius. Record the temperature in your data table and then replace the thermometer in the calorimeter. hydroxide solution into the calorimeter cup and stir gently. Place the lid on the calorimeter. Watch the thermometer and record the highest temperature in the data table. When finished with this reaction, pour the solution into the container designated by your teacher for disposal of mostly neutral solutions. Clean and rinse all equipment before continuing with the next procedure. Pour about 100 milliliters of the 0.5 molar hydrochloric acid solution into the graduated cylinder. Measure and record the volume to the nearest 0.1 milliliter. Pour the hydrochloric acid solution into your calorimeter, as shown in Figure C. That's in your lab. Measure and record the temperature of the HCl solution to the nearest 0.1 degrees Celsius. Immediately place the NaOH pellets in the calorimeter and gently stir the solution. Place the lid on the calorimeter. Watch the thermometer and record the highest temperature in the data table. When finished with this reaction, pour the solution into the container designated by your teacher for disposal of mostly neutral solutions. order to add our data to our report. In order to answer the questions regarding starting temperatures and temperature changes, we will need to include temperature change data in our data table. We'll represent that as delta T. And we get those numbers by subtracting our initial temperature from our final temperature. So what was the initial starting temperature of your distilled water, and what was the temperature of the distilled water after adding the sodium hydroxide? Our initial temperature was 19.5 degrees Celsius, and our final was 26 degrees Celsius. What were the temperatures of the 1 molar sodium hydroxide solution, the 1 molar hydrochloric acid solution, and the solution once combined? Well, turned out that both our hydrochloric acid and sodium hydroxide solution were 20 degrees Celsius, so our average was still just 20 degrees Celsius, and our final temperature was 25 degrees Celsius. What was the starting temperature of the 0.5 molar hydrochloric acid solution, and what was the temperature of the solution of the 0.5 molar hydrochloric acid and solid sodium hydroxide? Our initial temperature was 20 degrees Celsius for our hydrochloric acid solution, and then once we added the sodium hydroxide pellets, our final temperature was about 31 degrees Celsius, which was a delta T, or change in temperature, of 11 degrees Celsius. What was the mass of the liquid in each reaction? Well, since we had an aqueous solution, we're going to go ahead and use the mass of water, and each of our volumes was 100 milliliters. So water is 1 gram per milliliter, giving us 100 grams for each of the 3 reactions. So the mass of the liquid was 100 grams in each reaction. So how much heat was released in kilojoules in each reaction? In order to determine that, we will need to use our calorimetry equation. So we will divide our page up into 3 sections, one for each reaction. Here in each section, we will include the equation, our delta T, which was 6.9 in the first reaction, and then we will use our equation, heat equals mass times change in temperature times the specific heat of water. And for our first reaction, we got 2.9 kilojoules of heat. And in our reaction 2, we got 2.1 kilojoules, and in our reaction 3, we got 4.6 kilojoules. How much heat was released in kilojoules in each reaction? Right there, reaction 1, 2.9, reaction 2, 2.1, reaction 3, 4.6. Consulting the charts below, could the second reaction, where we had our aqueous NaOH and our aqueous HCl producing water and our aqueous sodium chloride, have evolved enough heat to cause an instantaneous burn? Well, our delta T for reaction 2 was 5.0 degrees Celsius, so our change in temperature was only 5.0. And if you remember, our starting temperature was 20 degrees Celsius. So 25 degrees Celsius was the warmest reaction 2 got. And if we look at the chart here, we don't even see 25 degrees on there. That's because 25 degrees is a little above room temperature, around room temperature. So our answer would be no, not enough heat has evolved to cause a burn.
I rule for the defense.